Welcome to an episode that's got it all. Particle systems, VEX, and Newtonian mechanics. Dobromir of In Life Thrill Design pointed me towards this GIF and this quite interesting Tumblr, and he asked me how to create this or how I'd go about creating something similar. Although I didn't quite come up with 100% exactly the same thing as this, I still like my results very much and would like to go over creating and implementing a custom particle system in Houdini with you. And in order to understand better what's going on, let's first talk a bit about math and physics behind it. So the first thing that we need to know is the conversion of the radius and the volume of a sphere, because what we're dealing with in the particle system will be spheres in the end. So these two very useful formulas are very helpful for our future particle system. On the one hand, this is how we calculate the volume of a perfect sphere from its radius here, and this is the inverse of it, so calculating the radius from the volume of the sphere. The second thing we need to look at is Newton's laws of gravity, and it works like this. When you have two masses spaced a distance apart from each other, this is how you calculate their attracting forces, the forces that push them together. So they are basically dependent from the particle's mass and from their distance. Also, they are dependent from what's called the gravitational constant, which I will talk about when we implement this. So in vector form, Newton's gravitational laws look like this. You take the distance vector, so a vector pointing from one particle to another, and put it into that formula that we already discussed. However, with the difference that we input only the length of the vector here, so the distance really that these particles are spaced apart, and multiply it by the normalized vector, so by the direction. What we're doing here is we are calculating the length of the vector and use that in our original formula, and then multiply it by the normalized vector in order to regain the direction. And finally, what we need to know is that we can calculate the acceleration by dividing the force that we just derived from Newton's laws by the particle's mass. So these are the basic formulas that will help us build the physics of our particle simulation. So let's talk a bit about how the actual simulation is going to work. And let's have a look at these two particles first. Each particle has a position, a vector called a for acceleration, and a radius called p scale, which is the size of the particle. The first thing we're going to do in our particle simulation is update the acceleration vector. So using Newton's laws and Newton's formulas that we discussed previously, we're going to calculate the gravitational forces between our current particle and all other particles in the system, and add them up together and update our current particle acceleration vector. We do that for all particles. After that, let's update our particles' position and move them along the acceleration vector, and then check if our particles are intersecting. And if they are intersecting, then we decide to delete the smaller particle of both, and finally update the remaining particle's acceleration vector by adding together both previous acceleration vectors proportional to the individual particle's mass. This is our basic particle system, so let's start implementing. The first thing we're going to drop down in our GeoSub is going to be a circle. And let's put this on the ZX plane and increase its radius. Zoom out a bit, and let's scatter some points in the circle. Maybe like this. Increase the relax iterations so it gets spaced apart evenly. Now that we have our initial particles, let's create a point wrangle. And in the point wrangle, set up our initial attributes for our particles. So for later, for shading, I'm going to give it a float called emit. And let's set that to 0 for now. I'm going to use that later in shading. Let's set up a vector called a for acceleration. And I'm going to initialize it to be 0 as well. Curly brackets here for defining a vector. And then let's set up a random p-scale value here. So add a float called p-scale and make it a random number and use our current point number plus a channel with an integer that we will call seed as our seed for our random generator. Let's click this button here to create the slider, and we can see we got our integer slider here, so we can change the seed. Also, just for quick scaling purpose, I'm gonna scale the p-scale by a factor, so I multiply it times 0.4 just to scale it down a bit. And the last attribute my particle needs is the mass. So again, a float called mass. And what I'm going to do here is just use this volume formula to calculate the sphere's mass. And I'm going to use a neat little trick because 4/3 times pi always remains constant. So I'm just going to calculate that by hand, put it into the formula, and then multiply it only by r cubed. So by p-scale cubed. Let's do that by cubing our p-scale first. So power p-scale comma 3 raises p-scale to the third power, so that's cubing it. And we multiply it by 4/3 times pi, which is the same as writing down 4.18879. And I calculated this number just by using a standard calculator and putting in 4/3 times pi. Okay, now we're set up to actually write our particle system. Let's just check in the geo spreadsheet. And yes, we have our vector A, we have a position, we have our emit for shading, we have a mass and a p-scale. Perfect. One thing that I'd like to do before going into building my particle system is relax the particles again, because now they have a p-scale value written on them, so they might be intersecting when we clone spheres on them. So let's just drop down a point relax, wire up the points. As my points don't have normals yet, just check relax in 3D space and increase the point radius scale a bit, so that the points will be spaced apart even more than the normal radius. 1.5, so they are getting pushed apart a bit further. And let's increase the iterations here as well to say something really high, so we make sure they are not intersecting at the beginning. Okay, next drop down a solver. And in the solver, the first thing I want to take care of are intersections of particles. So I'm going to drop down a point wrangle. And what I want to do is use this point wrangle to check if points are intersecting each other, and if so, delete them and update their acceleration vectors. So let's first find intersecting points by using a function called pcfindRadius. Let's create a variable called closept here, and it's going to be an array, so it's going to be a list of integers, a list of point IDs. We're going to use the pcfind_radius function here to find those points, and we're working on the 0 input slot, working on the position channel, and we want to take into account the p-scale value that the particles have with them. Then a scaling factor for p-scale, then the current position we're searching for the other points from, then the radius within we would like to look for other points. So let's take the p-scale here again, and then the maximum number of points, in our case 2. So what the pcfindRadius will do, in contrast to the standard pcfind function, it will look within a given radius for points that not only are within this given radius, but also for points which are intersecting in this given radius within their circumsphere. So they actually take into account the scale of the points and not only work on infinitely small points, but rather on spheres. So what this function will basically do is detect the intersection of spheres within a given distance. Exactly what I need for my particle system. So the next thing we're going to do is check if we actually found points that are intersecting each other, or rather found spheres that are intersecting each other, with the help of an if statement. And we're going to check if this array has a length greater than 1. Because what this will find is, on the first position in the array, it will find the points from which we're looking itself. So the current point we're working on will be written into this array as well. And that is why we're looking for 2 close points and not only 1, because the first close point will be the points we're working from itself, and the second close point will be a given collision. Okay, let's check if our closept array is bigger than 1 element, and if it is, let's first get the position of the colliding particle by creating a vector. Let's call it closepos, and it's gonna be our position of the point that's in the second list entry in the closept array. Again, the array's indices start from 0, so an index of 1 will yield the second entry in my closept list. We'll also get the mass of the colliding particle. Using the same technique, but just looking for the p-scale value now. Also, let's import my colliding particle's acceleration. And now we can start calculating our resulting vector A, so the acceleration after both particles are merged. And I'm going to use a formula that describes a perfectly inelastic collision here. And this formula goes like this. I'm going to create a vector called the sum of A's. And it's going to be our current particle's mass times the acceleration, plus our colliding particles mass times our colliding particles acceleration. And we will divide this by the sum of both particles' mass. Okay, that seems to run. Now that we've checked if particles are actually colliding, and if they were colliding, we calculated their new resulting acceleration vector, let's delete the smaller particle of both. Gonna use an if statement again here to check which particle is bigger and which is smaller by just comparing their mass. So if my current particle's mass is bigger than my colliding particle's mass, let's remove the colliding particle then, by using the remove point function. Like this. And update our current particles' acceleration and mass. Also for shading, what I want to do is, as soon as I detect a collision of particles, I want to set the emit value to 1. So they can glow later, as soon as they collide. So this is the case if my current particle's mass is bigger or equal than the colliding particle's mass. For the other case, let's remove the other point and update my colliding particles attributes. This time we have to use the a bit more complex set point attrib syntax, as we're not working on our current point now, but on the other colliding particle. And one thing that's just occurring to me, I'm not sure if this is going to work because I'm trying to access a particle attribute from a particle which I deleted previously. So I think I have to calculate this here before deleting this particle here. So let's just cut that. And create another variable called mass sum. And this needs 3 S's. Also, I'd like to update the acceleration vector. And the emit value. Like this. So after I've solved all the collisions, next thing I'd like to do is actually calculate all the forces. Again, using a point wrangle here. Just gonna create some variables that I'm gonna use. Just accessing my acceleration here. Initializing a new direction vector here. And a normalized directional vector here. So now what I want to do is find every other point there is in my particle system and calculate the gravitational force affecting my current particle and this particle by using the particle's mass and particle's distance. So let's run over all the other points with the for loop now. So this for loop will run from 0 to the maximum point index here and increase by 1 each loop. And we want to execute the code that's in the for loop only if I is not our current point number. So let's check for that. If I is not equal to ptnum, then let's do this. And what I want to do first here is calculate the vector pointing to the other particle. I'm going to do that by using the direction A vector that I specified. And just subtracting our other point's position from our current point's position. Like this. What I want to calculate now is the length of this vector. And I also want to normalize my directional vector so I can use it in the formula for the gravitation. Okay, you got a typo there. Like this. Let's create another two vectors for our current points and our corresponding points mass. And now we're all set up to calculate the resulting gravitational force. By multiplying our both masses and dividing them by their squared distance. So again, we square the distance by using a power and raising it to the power of 2. And then we multiply this again by the normalized direction to introduce the direction in our vector again. And the only thing we're missing is our gravitational constant. And if we were to simulate real-world physics, we would need to look it up and input it here. However, what I found is that I can use this gravitational constant to drive how fast the simulation is running. So I'm just going to use an abstract number here which has nothing to do with the real-world gravitational constant. I'm just going to abuse this constant to drive how fast my simulation is moving. So for starters, I'm just going to use minus 0.1 here. So from this force, we can calculate the acceleration. So acceleration for particle A is the force divided by the mass of particle A. And all I have to do now is update my current particle's acceleration by just going A equals A plus the newly calculated acceleration. So after we've run through all this and iterated through all our other points, we can write the resulting new acceleration vector back onto our point attribute. Like this. And the final thing I have to do now is update my particle positions using the acceleration vector that we just calculated. So again, I'm going to use a point triangle, and we will update our current point's position by adding to it our current acceleration vector. Also, what I'd like to introduce here is some form of damping, so our particles actually slow down if they are not encountering any other collisions by just multiplying our acceleration vector by a constant, in our case, say, 0.99. So each solver step we will take out 1% of that acceleration vector. Also, I need to update my particle scale using the particle's mass, and this time we're going to use this formula here to calculate our new particle radius, in our case called p-scale, and we will just use this formula, again substituting this term here by a constant that we previously calculated. Gonna update my p-scale by taking the cubic root. That's done with a command called cbrt, cubic root of my mass, which is equal to my volume in my case, and dividing it by that constant that we calculated previously, like this. What I also like to do for shading is make sure that my emit intensity decreases over time. So I'm just going to subtract a small value from it each step. And the last thing I need to take care of is to make sure that my emit does not go above 1 or below 0 by clamping it. Now let's go back up again with our solver highlighted, hit play. Well, that looks astounding. So let's drop down a copy sub and a sphere to visualize our particles and their scale. Let's just toggle the real-time switch here. Okay, there's something dodgy here. Let's try and find it. Alright, I think I've found several issues that were causing it to behave erratically. On the one hand, I scaled down the general p-scale a bit, so exchange the 0.4 by 0.1, so it makes our particles a bit smaller to begin with. The other thing, and I think this was the major cause of it not working, was in the solver. When we were dealing with the collisions, on the one hand we had this formula wrong here. This should be a multiplication instead of an addition. And also we're reading in here the wrong attribute, so this should read in the mass and not the p-scale. And when we change those attributes and hit play again, now our simulation looks much more solid. So now that we have our initial simulation, let's talk a bit about rendering this. So I'm going to go up to the geo level, drop down a grid, scale this up a bit. Also by control clicking on the environment light, I'm going to create an environment light and going to assign an HDR. And in the shop context, I'm going to define two shaders, two mantra surfaces in our case. And let's dial up the diffuse intensity on this. And dial down the reflection intensity. And increase the reflection roughness here. And we will assign this to our backdrop here. So let's put that onto the grid. And we're going to assign the other material to our particle system. Last thing we need in the output context is a mantra node. And under the rendering tab, we will set it up to use the physically based rendering. And also under the limits, I'm going to dial down the reflection bounces and increase the diffuse bounces a bit. Now the last thing I need is a camera. By control clicking on the camera symbol here, I will create a camera with my current view. Let's just translate this a bit so it'll look straight down on my particle system. Like this. And go to our render view, hit render. So let's work a bit on our particle material here by, on the one hand, increasing the diffuse color, and on the other hand, taking into account that emit attribute that we created on the simulation, so that as soon as particles collide, their emission gets set to 1. So to take that into account, we right-click on the mantra surface node here and hit allow editing of contents. And now we can dive into the mantra shader here. It's looking quite intimidating at first, but it's rather straightforward. The node we're working on is this. This is the main surface node here. And what I want to do is I want to use my emit attribute to drive the emit intensity here. And the way I can import and access an attribute in a mantra surface node is pretty straightforward. It basically works the same as importing a custom attribute into our point VOPs by just dropping down a bind node. And within the node, we will specify the parameters name, in our case emit, and it'll be a float, and we'll just wire this up to the emit intensity slot in here. Let's go back up one level, and within the emission tab of my mantra surface, I'm gonna enable emission, and I'm just gonna use the default white here for now. So let's just hit play on our simulation and see that we find a frame where some particles have collided, maybe like this. Go to the render view again and hit render. Not too much to see yet, and that is because I forgot one very important thing. Within my particle geometry, the copy sub currently is not set up to promote the attributes that I created on the template points here. So the resulting primitives that the copy sub is generating from my sphere and my template points will not have the emit attribute on it. In order to enable that, we're just going to go to the attribute tab and check the use template point attributes. And in our case, let's delete all this and only promote emit in my set tab. Let's check in the geo spreadsheet, and there is my emit parameter. Okay, back to my render view, hit render again, and we can now see we have collision points that are emitting light. So what we actually built here is a particle system with particle-particle collision and Newtonian gravity. Also, in the original GIF that I shown you that started this all, I think there are several parameters which are implemented not correctly, and intentionally so. So for example, what we could do if this Newtonian motion seems a bit too boring for us, we could go into the solver and into the point wrangle where we'll calculate the gravity. And for example, in here where we update our acceleration, just not divide our force by the particle's mass, which will yield very interesting motion patterns. Although we might have to increase our simulation speed by going in here and increasing the magnitude of my gravitational constant here. Maybe even more. So the particles are now swarming a bit more. So what you can do with this simulation is intentionally try and breaking it and try to play with the parameters, try to play with the formulas calculating the forces interacting between the particles, and thus come up with totally new particle behaviors and renderings. So a very versatile, very open setup. I hope you had fun with this. I hope I have sparked some interest in you with the basics of physics, because they're really interesting and really useful when dealing with particle systems. If you create any artwork using this technique, drop us a line. Always intrigued to see what you guys come up with. And it's cheers and goodbye.